The United States consumes over 4 trillion kilowatt-hours of electricity every year, but the sprawling network delivering that power is breaking down. Roughly 70% of U.S. transmission lines are more than 25 years old. In the field, that looks like this: leaning utility poles and fragile equipment that has already exceeded its intended design life. This aging infrastructure has created a massive bottleneck for new energy. There are currently 2,600 gigawatts of proposed clean energy and storage projects waiting in queues, unable to connect to a system that lacks the capacity to receive them. The grid was designed as a one-way highway, moving power from large plants to distant homes. Modern technology forces it to be a two-way street. Rooftop solar panels and electric vehicles push power back into the system, overwhelming analog controls. Understanding how to fix this requires looking at how the grid was first built. The engineering required for the future actually mirrors Thomas Edison's original vision: a highly localized, decentralized system of power. In 1882, the first commercial power grid launched at the Pearl Street Station in Lower Manhattan. Thomas Edison's system used direct current, or DC. Because DC power could not travel efficiently over long distances, generating stations had to be located within a mile of the user. This created a naturally distributed network of small, local power hubs. This localized model changed during the War of the Currents, when Nikola Tesla and George Westinghouse proved that alternating current, or AC, could solve the distance problem. The engineering breakthrough that ended the era of local DC power was the transformer. Transformers allow for efficient long-distance travel by spiking voltage high for the journey, then stepping it back down to safe levels before it enters a home. The transformer enabled the grow and build utility model. Society moved away from local neighborhood grids toward massive centralized plants, like the Niagara Falls stations, capable of powering entire regions from a single distant location. By 1960, this centralized architecture achieved near universal electrification across the United States. However, this scale was achieved by trading away the resilience of local, independent generation. The vulnerability of a megagrid became clear during the 1965 Northeast blackout. A single failure in a transmission relay cascaded across the entire interconnected system, leaving 30 million people without power. Maintaining reliability on this scale required precise electronic control over energy flows to prevent minor errors from becoming regional disasters. This ushered in the era of power electronics. Using solid-state devices like thyristors and IGBTs, engineers gained the ability to convert current, manage extreme voltages, and physically steer electricity through the grid's complex pathways. Power electronics stabilized the 20th century grid, but they were still operating within a one-way, centralized architecture that is now struggling to manage modern demands. The centralized analog architecture of the last century is struggling to keep pace with modern electrification. When millions of residential solar panels feed energy back into the network simultaneously, they create voltage spikes. The transformers installed in the 1960s were not designed to handle these reverse flows. Charging an electric vehicle adds a massive, unpredictable load to the very edge of the circuit, further straining local equipment. The solution is a shift toward microgrids. These are localized systems that generate and manage their own electricity, allowing neighborhoods to operate independently from the main grid when the central system is stressed. Building these microgrids requires new tools, specifically wide bandgap semiconductors like gallium nitride and silicon carbide. These materials allow for high-speed, efficient power conversion directly at the point of use. Managing this multidirectional flow requires artificial intelligence to instantly balance supply and demand across millions of connected devices in real time. The grid is transitioning from a static distribution line into a network of interconnected, autonomous nodes. 20th century engineering achieved scale through massive centralization. The current challenge is to provide resilience by successfully integrating the decentralized tools Edison first utilized over 140 years ago.